Today, it's going to be a little bit special kasi tuturuan ko kayo ng probability on steroids. Dahil gagawa tayo ng probability, o magkukulit tayo ng probability from simple probability all the way to two-way table probability. And if you want to know more about probability, just stick around at manood kayo ng video ko. So we're going to be working on probability. So the probability lesson that we're going to have will be a crash course on AP Stats probability. So we're going to go with the basic. So understanding probability is like learning how to work out calculus problem. You're not going to be able to answer derivatives if you don't know how to factor. And you're not going to be able to factor polynomials if you don't know your multiplication table. So similar to probability, it's actually really simple if you know your fundamentals and your basic. And since statistics and probability are together, this is where it requires you to actually understand the language that we're using. The first thing that you need to understand is the sample space. I hope that you have an idea of what sample space is. Sample space in statistics is basically possible outcomes in a given experiment. Now, in probability, experiment is going to be a little bit different because it's not like biology experiment where you need to dissect a cat. Experiment in statistics involves an example of one, flipping a coin. Flipping a coin in an experiment in statistics. And when you have an experiment in statistics, there are several events that you could possibly have in flipping a coin. For example, an event would be, what's the probability that when you flip a coin 3 times, you will get heads, heads, heads? That's one event. What is the probability that when you flip a coin 3 times, it's going to be tails, head, tails? So those are the events in an experiment. So we could have different events in different experiments depending on the questions. And you need to know your sample space to be able to answer all those probability events that you'd be asked. Another experiment that is popular in statistics, rolling a die. Rolling a die is another experiment. Rolling 2 dice is also another experiment. And it's a different experiment because the sample space will be changing. Okay, sample space. Since we're talking about sample space, do you have any idea what sample space is? So what's the sample space for flipping a coin? Just a single coin.
Heads or tails.
Heads or tails. So HT, 1, 2, we have 2 sample space in flipping a coin. What about rolling a single die?
1, 2, 3, 4, 5, 6.
1, 2, 3, 4, 5, 6. So it's just 6 sample spaces. What about if our experiment is on using a standard deck of cards? What will be your sample space in a standard deck of cards? How many cards do we have?
52.
52. Because how many suits do we have?
4.
4 suits. And for each suit, there are 13 different cards, right? Right?
Mm-hmm.
And that's why we have 52. Alright, so we're clear about sample space. So let's try answering some probability question involving sample space. So for example, we're going to find the probability of getting a number less than 5 when we roll a single die. So our experiment is rolling a die, and our event is a die that is, or a dot that is less than 5, right? So in classical probability, this is an example of classical probability because it involves sample space. Answering this will be simple if you know your sample space. And your sample space is 1, 2, 3, 4, 5, 6, right? Mm-hmm. So classical probability has a formula, and the formula is obviously in fraction form. And one of the properties of probability is that the value of your probability is always between 0 and 1. So your answer, any probability questions in a classical probability, your range of value or range of answer will just be between 0 and 1, and anything in between. 0.5, 0.3, 0.25, 0.8, depending on the experiment, right? Okay, what's the probability of getting a number less than 5? Let's construct our denominator. The denominator is always your sample space. And what is your sample space, or how many is your sample space for rolling a die? So your sample space is always going to be the denominator, and your numerator is going to be the number of success in a certain event. So the event is number less than 5. Can we consider as the number of success?
4.
We have 4. So numbers 1, 2, 3, and 4 will be our number of success. So the probability of this particular event happening in statistics is going to be 4 out of 6, which we can also simplify, right? 4 out of 6, if we simplify it, is going to be 2 over 3. Now, in AP statistics test, sometimes they don't simplify, sometimes they use the decimal value. So make sure that you know how to use your calculator to change this in decimal value, because 4 over 6 and 2 over 3, if you use your calculator, it will just be the same, right? So take note of that, that sometimes they give you their value in fraction form, sometimes they give it their value in decimal form. Alright, pretty simple, right? Now, the level of difficulty in a probability is dependent on the experiment. If the experiment is pretty simple, answering probability in that experiment is also simple. Rolling a die, anything that has to do with rolling a single die is easy. What's the probability of getting an even number when you roll a die? 3 out of 6, because there are 3 even numbers, 6 possible outcomes. What's the probability that you will get an odd number when you roll a die?
3 out of 6.
It's the same thing. What's the probability that when you roll a die, you'll get a 7?
0 out of 6.
0 out of 6, or 0. That is why your probability is always in between 0 and 1. So if the question is, what is the probability that you will roll a die that is less than or equal to 6? 6 out of 6, which is 1, right? So that's why you need to know or remember that one of the properties of probability, which is the sum of all the probabilities in a certain experiment, will always equal to 1. Alright, let's make it a little bit more challenging. How is it going to be more challenging? Look at this situation. So, let's talk about sample space. Again, sample space, when you're visualizing it, it's easy and simple. Rolling a die, you can visualize it in your head. However, this particular experiment will be a little bit difficult to visualize, right? Why? Give me a possible outcome of a couple having 3 children. This is one possible offsprings for 3 children, right? Give me another one. Girl, girl, boy. Now, we need the exact number of possible outcomes in this probability so we can compute for the probability of this event. So we need our x and we need our sample space. Sometimes finding the sample space is difficult and finding the number of success is also difficult, just like in this particular example. That's why we're going to understand the value of a tree diagram, because we need to find the probability of this particular event, right? So what is the tree diagram? It's a visual tool that you could use so that you can visualize all your sample space. Probably getting 2 consecutive boys. So that means you need to have B, B, and B or G, right? And this is your X, or your number of success, right? But the problem is, how are we going to figure that out visually? All right. So the concept of this particular probability is pretty much the same as flipping a coin. And you're flipping a coin how many times?
3.
3 times, because you need 3 children, right? So that's what we're going to be producing. So the first flip, or the first child, what's the probability of our first child? It's either
Boy.
or.
Girl.
So we have 2 possibilities for our first offspring. The second offspring
Boy.
will have another tree diagram, which is also B, G, and a combination of another B and G for this possibility, right? Since we need 3 children, we're going to be using 3 sets of branches. That gives us BG. And if we need 4 children, we need to branch another one or have another branch for this tree. If we need 10 children, then our tree will be bigger. Got it? So since we only need 3 children, we need this diagram. And the reason is, having this diagram, it gives us a more visual representation of the sample space, which is going to help us not to miss any of the sample spaces. So we have B, 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 right? And we have
B, B,
B, B, G, all the way to G, 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 right? So how many do you think is our sample space in this probability?
8.
8. 1, 2, 3, 4, 5, 6, 7, 8. We have 8 probabilities. Now, in statistics, we have this thing called fundamental counting principle. And the fundamental counting principle is basically just multiplying the possible outcomes in an event. In this particular event, we need 3 children. And for each children, the probability is, the possible outcome is 2, right? So it's just 2 times 2 times 2. So this is the fundamental counting principle, or just multiplying or finding the products of your possible outcome for each event. So 2 times 2 times 2 is? Which is also the same as our visual. So what I'm showing you is a visual way on how you find your sample space and the mathematical way on how you use fundamental counting principle in computing for the sample space. Now, take a guess. Now that you visualize, sort of, your tree diagram and your sample space, what do you think is the probability of getting 2 consecutive boys? 25%? What is your fraction?
2 over 8.
2 over 3?
8.
2 over 8? So that there are only 2 possible outcomes?
Isn't it 3 though?
Isn't it 3? Why is it 3?
No, because it said...
Girl, boy, boy.
Girl, boy, boy? Is girl, boy, boy also consecutive?
Oh, I thought it was talking about like the first 2 set of boys. Like the first 2 are boys. Okay.
That's why in probability or in statistics, it's important that you're understanding what is being asked. So, reading comprehension will be tested on any probability experiment. So is it 3 out of 8 or 2 out of 8?
3 out of 8.
It's 3 out of 8. And again, knowing your tree diagram, just like what we have mentioned, will help you understand how your sample space is going to look like, because sometimes it's enough to just know your sample space as a numerical value, but it's even better if you have a visual representation of all the possible outcomes in an experiment. And the reason why you need all of these is because if you have all of these possible outcomes, answering any probability question from that particular experiment would be a lot easier because you have a cheat sheet. Basically, you're creating your cheat sheet for your probability question when you are drawing your tree diagram. And these will be your sample space. And when you have this sample space, you can now answer, give me 1, 2, 3, 4, 5. Fraction form. You don't need to change it in decimal form or percent form. Just give me the probability of these events. At kung gusto nyo malaman ng mga probability lessons ko dito sa channel ko, i-hit nyo lang itong I button na ito para mabigyan ko kayo ng mas marami examples kung paano magsagot ng probability from simple probability all the way to conditional probability. So, let's have the probability for each of these events. So we have 1, 2, 3, 4, 5 events. The problem getting 2 consecutive boys? What?
3 out of 8.
3 out of 8? Check. Getting a boy and then a girl?
3 out of 8. 4 out of 8.
3 out of 8 or 4 out of 8?
4.
Let's count. That's why we have these as our sample space. Getting a boy, then a girl. Yes, no?
No.
Boy and then a girl? No. Yes, no?
Yes.
Yes, no?
Yes.
Yes, no?
Yes.
Yes, no? Yes, no?
Yes.
Yes, no? Yes, no?
No.
So we have 1, 2, 3, 4 number of success out of the sample space. So classical probability, as abstract as it may seem, there's actually a process. That's why you need to know your formula, you need to know your number of success, and you need to know your sample space, and then boom, 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 you have your answer in each of these events. How about the third one? 1 out of 8. How about the next one? Of having a girl as a third child.
4 out of 8.
4 out of 8, because all we need to do is to look at these. 1, 2, 3. 3.
4.
Where? 1, 2, 3, 4. Yes, 4 out of 8. Having exactly 2 girls.
1 out of 8.
1 out of 8.
Wait, no, 1. 3 out of 8. 3 out of 8. I was thinking the first 2 were girls. Never mind.
Do you know why it's 3 out of 8? Exactly 2 girls? Alright, no boys. Alright, so this is how we make babies in statistics. Now, dependent and independent events. When rolling a die, what is the probability of getting a 2 or a 5? So, dependent and independent events are basically used to use math operations so you can compute for the probability. So, the experiment here is rolling a die. You roll a die. Boom. You got a 2. Success. You roll a die. Boom. You got a 5. Success. So what is the probability that when you roll a die, it's either a 2 or a 5? So the probability of the first event is what? Getting a 2 is our first event. It's going to be in fraction form, and it is, this is pretty simple. Don't overanalyze it. What is the probability of getting a 2?
1 out of 6.
Probability of the second one, getting a 5. Also 1 out of 6. So, OR operation is basically addition in probability. And in this case, it's getting a 2 or a 5 is 1 out of 6 plus 1 out of 6. So that's the probability that this will occur if you roll a dice this many times. Got it? So, P of 2 is 1 over 6. P of 5 is 1 out of 6. All you need to do is to remember how to add fractions. So, what is 1 6 plus 1 6? So, that is a probability of 1 over 3 of getting a 2 or getting a 5 when you roll a die. So another operation in probability that you need to remember is the AND operation. So how is it going to change if instead of getting a 2 or a 5, we have getting a 2 and a 5? That means you need to roll a dice twice. And it needs to be exactly a 2 and a 5. Which means when you roll a die, 2 dice, let's say, 2, 5 is appearing. And if you roll a die and it's 1, 1, it's not a success, right? So what's the probability that it will be exactly 2 and a 5? And in this case, we're going to multiply. So the AND operation is multiplication in probability. So it's pretty much the same as the OR operation. The probability of the first event, event A is
1 out of 6.
and event B.
1 out of 6.
So you're just going to multiply. And what do you notice in your answer? What's 1 out of 6 times 1 out of 6?
1 out of 6.
Smaller. So do you see why the chance or probability of this particular event is smaller than this one? Because one, either or, the other one, it needs to be exactly that. And this is only possible for events that's considered as independent. Now, why is this considered independent? We have a die. Why?
Because one roll of a dice does not affect the outcome of the other dice.
Yes. Unless you're going to erase one of the dots in your die on your second roll, then it becomes dependent, right? Independent and dependent events. Independent, example of them. Event A is not affected by event B. Tossing coin is an independent event because each toss is not going to change, right? So when you toss a coin twice, the outcome of getting H or T is the same on the first toss and on the second toss. So that means you can perform the addition and the multiplication principle for these events. Now, one is an example of a dependent event wherein the first event is affected by, or the second event is dependent on the outcome of the first event. This one. 5 red and 2 marbles in a jar. Right? What is the sample space here? The number of marbles. So how many marbles do we have? 7. So 7 marbles, we have 5 red and 2 blue. This is an example of a dependent event because the probability of getting the first red marble is 5 out of 7, right? 5 marbles in a jar. You pick one. So the probability of getting a red marble is 5 out of 7 without replacement, right? And what about getting the second marble? Do you understand why it's 4 out of 6 now?
Yes.
Because it's without replacement. But if it's with replacement, it is independent. So let's have another example of this particular rule in probability. Thank you so much for watching. This is Dr. Esperanza, and if you happen to like this video, i-like nyo na at i-share ang mga math videos ko para mas marami akong mga bata matulungan na kagaya nyo. See you again next time. Bye!